Good day and welcome to the Moscow Telecommunication Seminar. Let me briefly introduce our today's speaker, Pablo Serrano. Pablo Serrano is an associate professor at the Department of Telematic Engineering of University Carlos III of Madrid. He has over 100 peer-reviewed papers in international journals and conferences. He has participated in many national and European research projects. He is currently Deputy Director of Teaching Affairs at the Department of Telematic Engineering and the Director of Master in Connected Industry 4.0. Today, he will present us his talk about the performance evaluation of Google Loon service. Pablo, the floor is yours.
Okay, thanks so much. First of all, thanks for inviting me and thanks for attending this talk. And as you have mentioned, I'll present this work on the analysis of the performance of this Google Loon service that they were aiming at providing internet access using balloons in the sky. And this is a joint work that I've done with my colleagues that you see on the slide, Marco Gramaglia, Francesco Mancini, Luca Chiaraviglio, and Giuseppe Bianchi. So as a brief introduction to myself, to add on what you already mentioned, I'm an associate professor at University Carlos III of Madrid. I'm the director of this Master in Connected Industry and associate editor of the IEEE Open Journal of the Communication Society. Right now, I'm involved in the flagship European project HexaX, which is on the evolution of 5G to 6G. I'm interested, of course, in 5G and 6G. Wireless communications, test-based performance analysis. And also I've been enjoying performing a number of visiting researcher positions at different universities, in Massachusetts with Jim Kurose, in Barcelona with Jan Gruenberger, in Dublin, and so on. And what's interesting or relevant about this job is that this work, is that I started looking into the Google Loon project as early as 2013, when the project was kicked off, as I'll summarize later on. And it was only now in 2020, when we finalized doing this analysis, when we were able to properly specify the problem that we were trying to solve and the performance figures that we used to analyze this service. In case you didn't know, the Carlos III University of Madrid is a relatively young university by Spanish standards. It was founded in 1989. The first chancellor was Gregorio Peces Barba, which is one of the fathers of the Spanish Constitution. It's a mid-sized university for Spanish standards with a target enrollment of approximately 20,000 students. And it's doing pretty well in terms of grades, as the student and community students typically have the highest average grades in Madrid. Plus, we are also very international, where 20% of all of our students are not Spanish, are from abroad, in Europe, but also Latin America and other continents. And of course, this internationalization, is higher at master studies and also at the PhD programs. And even counting for nationals, approximately half of our students have done some sort of mobility program, typically an Erasmus placement program. And the university is also doing pretty well in terms of employability. Like the recent statistics, 90% of our graduates, they found a job related to the area in less than 2 years. And in terms of research, we are among the best universities in 6 different fields. So you have, of course, my coordinates as of now and also later after the talk. And of course, I'm always looking for people to motivated to collaborate with. So coming back to today's topic, to the analysis of the Google Loon service, let me first introduce, for those of you that are not familiar with it, the Google Loon project. The motivation was that nowadays we are talking about most of the developed world heading towards the realization of the gigabit society, that we are having faster and faster speeds to connect to the internet, but still approximately half of the world population don't have any internet connectivity. And the problem is that, as this half of the population, these billions of people, are living in rural places. There is no network to improve because there is no infrastructure. And in order to deploy the infrastructure, there are severe geographical challenges such as jungle, archipelagos, or mountains. So in order to reach these billions of people that they don't have any internet connectivity, the proposal by Google was to use balloons. As these are flying objects, you can think of them as flying cell towers, and therefore there is no need to wire them. There is no need to deploy a wired infrastructure to connect to the internet, and since they are powered with solar panels, there is no need to wire them also to provide them with electricity. There is no need to power them with power. So the idea with the balloons is to beam internet access, so to deploy these balloons on top of the population that you want to provide coverage. And then from top of these balloons, you beam internet access downwards to this population. And by just using wind and solar power, the balloons may go up and down. The idea is that the balloons, they are filled with a lighter than air component. So the more of this gas that you have, the higher the balloon goes, and the less you have, then it decreases the altitude. And playing with this variable, how much you want to go up and down in altitude, and the winds in the stratosphere, then you can do, as I'm showing in the slides, these are the so-called figure 8 flying patterns. So you want to stay, for instance, in a given location, you go up and down to move a bit to the left and a bit to the right, but eventually on average you're staying approximately over the same surface. Because the balloons, and I will emphasize this, in contrast to other drones, in contrast to other architectures for UAVs, in which you have engines so they can be steered, the balloons are completely passive in the sense that they can only go up and down in the atmosphere. So you need to gather weather forecast prediction to know how the wind's going to change, how the wind's going to blow. And based on that, the balloons will be running, some machines on the ground will be running AI algorithms to predict the winds, and based on your intended destination, to tell the balloon whether to go up or down to try to reach that destination. So, for instance, if you want to travel, the balloons, they don't travel in a straight line, but rather they do these strange loops. So they can go up and down and catch the most convenient wind to reach their destination. And the idea is that eventually the AI algorithms progressed. This wasn't designed by humans, but rather was an AI algorithm anticipating the forecast of different regions and then doing this strange flying path to reach their destination in the shortest time. With that, the architecture is the one illustrated in the picture, in which the idea is to have a network of loons that they can connect both ground, they can provide internet coverage and they can transmit to the ground. And there are also the interloon loops, with the idea being that if the users in the rightmost figure, if the users are connected to a 4G network on the loon on the right, but this balloon doesn't have internet access, but rather it needs to go 2 hops to the loon of the left, in which that loon can now connect to some gateway that is providing the internet access. The idea was, at the very beginning, they were going to use the ISM band. Their plan was to use some sort of Wi-Fi-alike technology, but eventually they decided to switch to LTE, since using 4G plus reaching agreement with neighbor operators, it really simplified the interference problem, since they were given some frequencies in which they were the only radio network to transmit. While most of the balloon is gas, most of the width is about the balloon itself to keep the thing up in the air. They are attached the solar panels and a box. And in this box, they have the batteries, the circuit boards, the navigation, and the LTE equipment. And typically a balloon covers a region of up to 40 kilometers in radius. And one of the key advantages of this project is that since the balloons are up in the air 20 kilometers above the ground, there is very little probability of having interference with buildings or with other typical causes of interference in urban environments. So it's safe to assume that this is a free space propagation. Plus the interballoon links. There are papers from Google in which they report that they can reach interballoon links of up to 100 kilometers. These are in the last stages of the project. These interballoon links were based on on laser. So they were having some complex algorithm to properly align the lasers. Of course, at such distances, alignment is critical, and they were able to interconnect the balloon even 100 kilometers apart. Officially, the project was announced in this blog post in June 2013. So in the city of Christchurch in New Zealand, they deployed the first relatively large experiment in which they deployed 30 balloons to try to connect 50 mobile phones on the ground. And at the beginning, well, apart from these impressive and nice pictures, this launching was a very manual process. In the picture, you can see a number of Loon employees with the solar panels and waiting for the balloons to fill with this gas to start the launching of the balloons. This is an image from the launch in New Zealand. Then as the project evolved, they were automatizing the launching process. And then in Nevada, in the United States, eventually they were automatizing the project. They also reported that by automatizing this launching of balloons, they incurred in less problems, in less accidents. And then in the picture, you can see that most of the balloon is about the solar panels that, according to their sources, in full sun, they're able to provide up to 100 watts of energy, which is enough to provide an LTE cell with energy and to recharge the battery for operation during nighttime. And then you also see below the solar panels all the boxes corresponding to the communications infrastructure. It's also remarkable that they were able to improve the lifespan of these balloons. So typically a balloon would last for hundreds of days, and the record was this balloon, this HBAL 703, which was up in the air for 312 days. It was launched from Puerto Rico in May 2019. It provided service for 3 months in Peru. This is where you see most of the scratches in the figure. And then after providing service in Peru, it did a circumnavigation across the Atlantic Ocean, the Indian Ocean, and then the South Pacific. And then it stood in. So coming back to this record that, they were providing, this Loon was launched from Puerto Rico, provided service in Peru, and then traveled all across the different oceans till it stood for 7 months in the Pacific, and then it safely landed in Mexico. And also the Google employees were very fond of this durability, because at the beginning the Loons lasted for a few months, and this one lasted for 10 months. And the idea being that they wanted the Loon for sure to stay up for as long as possible, as this should decrease the cost of maintenance of the service. But still, if you like anecdotes, the project is filled with anecdotes. For instance, some lands were more specifically crashes. And the problem is that at the moment Google lost connectivity to the Loon, then they have no control over it. So when it's going down, they cannot steer direction, they cannot control when it's going to land. So in the States, one of the Loons, then it took out some power lines, so causing some energy shortage. Also in New Zealand, they thought that a balloon was a crashing plane, so they have to, they call the 112 or the 911 and recover just the hardware. And it's also funny that in this post from Gizmodo, there is several collection of cases in which people think that these Google Loons were UFOs. So the picture on the left is in Colombia, the picture on the right is Sri Lanka. And since the project was not that much well known at the beginning, well, people were seeing flying objects and yeah, they were thinking about UFOs. And also these anecdotes serves to anticipate that managing this fleet of balloons that you don't have the intelligence is it's an artificial intelligence, so there is no human in the loop on the way they're going to behave. Plus, they may be fallible, so the loons may break and so on. You can guess that managing this project was filled with anecdotes and challenges such these ones. So now that I've introduced the Google Loon project, let me formulate the research question that we wanted to solve with this paper, and that is, okay, you are using Loon to provide an internet service. How effective and stable could be this service? So our question is, okay, there is a nice marketing to the Google Loon technology. There are some promising results. Google, I'll review later on, was reaching agreements with Telefonica, with Kenya operators, also in Puerto Rico with AT&T to provide emerging services. But how effective and stable can be this service? Can we put some numbers into the internet service? And to this aim, to answer these questions, we had to proceed in 3 steps. First of all, to gather data about the loons, where were deployed and over which regions you could have coverage by the loons. Then identify the use cases. We had to identify in which areas and for which period of time there was supposed to be coverage. So then compared to the ideal case, we can assess the performance of the service and also derive the performance figures. So we're talking about a communication service. We can think of throughput, downlink, uplink, delay, latency, you name it. But we decided to start with the most basic performance figure, which is downlink coverage. So how easy or how effective is this Loon architecture to provide you with coverage that you switch on your phone and there will be a signal indication from the operator that is broadcasting via the Google balloon. So I'll go step by step, with the first step being how we gather this data. And then how to track these loons. And this is something that I started in 2013 as I was in Barcelona collaborating with Jan Grunenberger. And the idea here is to realize that loons are flying objects, and because they are flying objects, they need to obey certain rules, which is they have to implement this secondary radar system, the ADS-B, and this transporter, for each loon is provided with a unique address. This International Civil Aviation Organization address. So this transponder, this radar, is announcing a unique address per loon, and also is announcing its latitude, longitude, the speed as a vector, and the altitude. And also, in addition to this unique address, the call sign, which is the flight number. So the international address is kind of the identification of the plane, and the flight number, it would be the identification of the flight. And for Loon, it was agreed that the flight numbers would start with HVAL. So with this, so this secondary radar system, this ADS-B technology, well, here you have a picture of the elements of interest for the navigation part, the loons on the left and all the components on the right. They have a parachute in case of emergency, and then there are the flashers, the transponder, and so on. The thing is that these messages of these secondary radar systems, they are easy to receive with USB sticks for digital television. And since these USB sticks are very cheap, the availability of this technology is the one feeding the crowdsourced initiatives such as RadarBox or Flight Radar 24, which are these web pages in which you can look for flights and you can check the routes, the destination, the current altitude, the speed, and so on of anything that flies, and also of the cars in the airport. So you, back in the day, Flight Radar 24 in a blog spot announced that they were able to track all these many loons that they were providing service to Puerto Rico after some hurricane that happened in that island that I'll cover later on. So here you see there are up to 6 different loons highlighted with the prefix HVAL and different numbers. And there are 2 extra loons in yellow that they don't have associated a flight number, but well, Flight Radar 24 is providing with this ability to track the position of the loons at any point in time. Well, you can, as anonymous user, you can log into Flight Radar 24 and see the current status of the aviation worldwide. But also, if you are a premium member, if you have a golden subscription, then you can go back up to 3 years of history. And the way to be a golden member is either to pay a monthly fee or to build your own receiver. So with a Raspberry Pi and an DVB-T USB stick, you can download a software and contribute to this crowdsourcing of information. And then you are given golden access, the business plan, that you can use to gather information from with a history of 3 years. So with this, we were able, as premium users, to access Flight Radar 24, and by looking worldwide, all the regions, and looking for, looking for in the news whenever they were launching a new project and looking for the Loon icons and so on, we were able to identify most, or we think all of the flight identifications with each HVAL, and then we were able to query the database of Flight Radar 24 to download the positions, latitude, longitude, the speed, altitude of the different loons across the globe. And with this, I can show you some general stats. So first of all, the most basic stats is the altitude and the speed. According to the data we gathered, the loon altitudes are between 16 and 20 kilometers, which correspond to the stratosphere. And this is what Loon is claiming. So it's a perfect match. They are claiming that the loons will be deployed in the stratosphere, which is twice the typical altitude of planes. And the thing is that in the stratosphere, well, if you go to the southern polar vortex, then there are wind speeds that are super high, like up to 200 kilometers per hour. According to some sources, they were claiming information from Loon. Typically in the stratosphere, the winds are relatively low, from 10 to 13 kilometers per hour. But if we plot the CDF of the reported speeds, which is the figure in red, we see that this is not exactly the case. Like for here, we're marking the medium, like 50% of the reported flying speeds are approximately 20 kilometers or less, but there is a relatively large amount of flights that they are reporting relatively higher speeds. So, and of course, the higher the speeds, well, the more difficult it's going to be to control on the one hand. So high speed is good to reach your destination as soon as possible, but also high speeds is going to result in challenges to keep the loon over the place that you want to provide service. We also counted the total number of loons per day and the total number of unique loons from 2016 onwards. So in blue, we have the total number of unique loons that we have seen with different addresses from the transponders. And in red, we have the average of the number of different loons per day. And here we can see that by 2017, we have a third spike with up to 40 simultaneous loons on the same day. And it's also interesting to analyze the slope of the number of different loons that we have identified. So before 2017, we had a growth rate of 400 loons per year. So here we infer that Loon was heavily, Alphabet was heavily investing in extra hardware to throw more and more, to launch more and more loons up to the air. But then during the later stages of the project, this growth in the number of loons was substantially reduced up to down to 25 loons per year. So at the beginning, we have a deployment of the service, and you could conjecture that this was more of a sustainment of the service, like to replace those loons that were crashing or couldn't be replaced. And if we plot where these loons were over the Earth's surface, since we're using crowdsourcing, using stations in the ground, we don't have data for whenever there is sea, or in the oceans or the seas, we cannot detect these loons. But whenever for the grounded coverage areas, we see more or less the equation of the loons. You can see that the higher densities, it corresponds to North America, where they were doing several test flights. Puerto Rico and Peru, that I detail later on, as use cases, and Kenya was one of the latest announcements. And also in Australia, since 2013, this is where the service was officially launched. And regarding the time it takes to deploy a given service, we didn't formally analyze this, but by computing the average speed, you can more or less approximate that from Puerto Rico, from Ceiba, this is the launching site in Puerto Rico, they were able to reach Peru in approximately 1 day, 20 hours. But if they wanted to reach Kenya, it could take the loon up to 5 days. So obviously it's not a service that you can deploy immediately, since it takes a bit for the loons to reach the intended destination. Okay, I already anticipated it a bit. Now, the use cases that we analyzed to try to assess how good the service was. So, of course, Loon announced their operation in different countries or regions, but there are no official announcements in the sense that they never claim, starting from this date, we are covering these specific regions with these square kilometers until this other date. So we had to guess. And basically what we did is to study the use cases or the application scenarios that were extensively reported by media. I already talked about Puerto Rico, Peru, and Kenya. And then we decided not to focus on the whole country or region, but in the case of Puerto Rico, which is very obvious, but only for those regions in which we had some non-zero coverage. And basically our threshold was that you should have at least 2 hours per day for at least 3 months. And then we defined the use cases in that way. So whenever we have a period of 3 months with cells that were provided with a given minimum average coverage of more than 2 hours per day, that would be our use case. And building on this definition of use case, we counted the number of loons over these 3 months. The first use case, and the most famous perhaps of the loon service, was in Puerto Rico, that they were having the Hurricane Maria that hit the island, and then it broke down all the communications. So then once the hurricane left the island in October, then the FCC authorized Google to provide coverage over the island. They partnered with AT&T and T-Mobile, and they claimed that more than 100,000 people were provided basic internet connectivity. If we look at the picture, here we are plotting the average number of loons per day. And we see that right after the Hurricane Maria, the number of loons over the island spikes, and you have an average of more than 6 loons per day. And then, as Google claimed, after March, once things were going back to normal, then the service started to wind down. You see that the average number of loons decreases sharply. And there is always some activity over the island because, as I mentioned, Ceiba, which is a city in the northeast of Puerto Rico, is a launching site of loons. So this was validating our methodology using flight radar, that we were able to correlate the activity that we gathered from the crowdsourcing scenario with that reported on the media. Well, Puerto Rico, as I mentioned, is rather straightforward. It is an island, and here this is where we detected coverage, basically over the whole island. And the total area is 9,000 square kilometers, and ideally you could provide coverage with just 2 loons. if you were able to provide 2 loons right on top of the intended destination and keep them there, then you will need just 2 to provide this 100% coverage. We'll see that this is not the case. The second use case was in Peru, in the so-called Loreto region. The collaboration with Luna Telefonica goes back to 2014. It was famous. Peru suffered from a number of natural disasters, El Niño flooding and an earthquake, but this didn't appear in our data set since these are catastrophes affecting the region in the coast. But they did announce that they intended to provide internet service over this Loreto region in the Amazonas, and they decided to create this neutral host, Internet para Todos, Internet for Everybody, operate. And as we see in our database, even if the agreement was announced in November of 2019, we can detect that there were spikes of up to even 10 loons over the region. The agreement, right after the agreement, we have a period of maximum activity, and then again we see that it seems this service is losing interest and less loons are happening over the region. The geographical region is in the Amazonas, as I mentioned. This is a jungle area of 46,000 square kilometers. And to put you in context, this is basically most of the Peru. You see some of the regions affected by the earthquake here, the Piura and Chimbote, which are in the coast. And of course, we were not looking in the coast. We only detected the activity in this National Reserve, Pacaya Samiri. And finally, for the case of Kenya, Loon announced that they were going to provide internet service in 2019, even if they already had some activities. Some loons were flying over Kenya in 2018. But the thing is, even if they announced that the service will start in 2017, we see no loons between 2018 and 2019. And it was only in 2020 when the Kenyan government gave approval for the development of the project. And in July, they announced that they were going to provide this service to connect remote areas in Kenya. And the target was to deploy up to 35 loons. And according to our data, well, you see in the figure that the average number of loons barely reached 4 over the area, which is an order of magnitude below the target figure of 35. Again, the region of Kenya is the one marked in green. To give you in context, you see here Nairobi and you see here the coast, so it's relatively indoor and less communicated. So these are the 3 use cases that we wanted to focus on. The second step is to define this performance figure. And as I mentioned, we decided to focus to coverage, which is the simplest and the most basic one, the one that you need to start building something more sophisticated. To estimate coverage, as I mentioned, we consider only a downlink scenario. And basically the idea is that we are assuming a free space propagation model. Since there is this paper published by Loon researchers in which they detail the assumption that they use to design their antenna, and we follow the same assumptions. An operation frequency of 800 megahertz, a transmission power of 37 dBm from the antenna, a negative gain, assuming that the mobile phone is in the pocket of your trouser of minus 10 dBs, and a transmission gain that is not omnidirectional, but has some lobes. It's reported on the reference one, and that we can, with these input parameters, we can, for every point on the ground, we can compute the elevation gain, the distance, given the altitude and the radius, and therefore compute what is the path loss. And we assume a sensitivity of minus 100 dBm. So this is our model to compute the path propagation from the loon to a station in the ground. But then we are not done just with announcing the formula for the coverage. We also decided to discretize time and space. More specifically, we decided to tessellate the surface and to discretize time to simplify calculations. And basically the idea is that if we can capture the movement of loons across different timestamps, as you see here, this loon flying from west to east, and then we have the surface tessellated in hexagons, then it's rather straightforward to compute an average coverage for each of these 3 time instants. At t equals to 0, we have 6 out of the 7 cells. At t equals to 1, 4 of the 7, and at t equals to 2, 5 of 7. And with that, we have an average over the surface, but we can also compute an average over time. If we are having equally sampled instance of time, then the average would be 1/3 over these 3 averages. So the challenge is to define how large this hexagon should be and what should be the delta of time. To decide the hexagon size to tessellate, we rely on Uber's H3 library. Uber, the car service, provides with a free library that tessellates the Earth in hexagons of different resolutions. And basically, we tested how the definition, the accuracy of the received power versus distance at 2 different altitudes of the loons at 15 and 20 kilometers with different resolutions. So for instance, if we pick the resolution number 6, then for this length, which is up to, well, some kilometers, we see that the step using this resolution goes from minus 97 dBms to up to minus 87 dBms. So we see that using this resolution, the difference in received power is more than 10 dBs, which is a lot. If we picked a more accurate resolution, the so-called resolution number 8 from Uber's library, then the difference between one step and the next one using this resolution is less than 1 dB. So it's too accurate, and this will result in too many points and a lot of computational complexity. That's why we decided to stay with this resolution 7 with hexagons on 1.4 kilometers. This is for the tessellation of the area. Then for the time discretization, the idea is that we don't want to use time as a continuous variable because, again, this is very complex. The idea is we take samples of this time. And our design criteria was that we don't want the loon to travel more from one instant to the next. We want the loon to travel at most 1 hexagon. So since we're using a resolution of 1.4 kilometers of radius of this hexagon, we measure the 99 percentile of the speed, which is 100 kilometers. So then with that, we can put a bound on the time step, which has to be less than 1 minute and 1 minute and a half. So we decided to set the delta of the time in 1 minute. And with that, we have the tools to compute the coverage of the service. Now we are assessing how efficient and how stable this loon service can be. So for the case of Puerto Rico, here we are plotting the daily coverage, the daily average coverage for 3 months. And well, as I think the picture speaks for itself, there are so many ups and downs. So the coverage only reaches up to 90% in a few occasions. The average coverage during the best 3 months that we could find was about 60%, but also there are several periods of time where there is 0 coverage, that no loon is provided coverage to the island. For the case of Peru, in terms of peak coverage, the situation is even worse, as in the best day, it doesn't reach an average coverage of 85% over that region that we selected, while the average coverage is more or less on 40%. And finally, in the Kenya use case, we see that, well, at the beginning, it had a bit of a slow start, the service, but during the last months, the coverage seems to have been maximized with peaks of about 80% over here. And the average coverage was something like 60% during the last month. So this is the first analysis that we did, and it showed that it seems it's very difficult to provide a good and sustained service over time. We also, as we saw that sometimes you have a few loons, or sometimes you have a lot of loons over the same coverage, we did a conditional analysis of coverage in which we plot the density of the coverage depending on the number of loons. So basically you have the coverage on the x-axis and the number of service loons over the area on the y-axis. So for the case of Puerto Rico, you see that whenever you have one loon, you could have from 0 to up to 70% of coverage with a median coverage of 55. With 2 loons, you can have a median coverage of something like 70%. And in some cases, you do reach 100%. As I mentioned, with 2 loons, if they were statically placed, you would reach this 100%. The more loons you add into the mix, when you're adding 3, 4, 5 loons, you see that the distribution, this density function of coverage, is skewing to the right as the service is improving. But still, it's challenging that even with up to 6 loons, the probability of less than 100% coverage or less than 90% coverage is still non-negligible. So you need up to 6 loons for the median coverage to be above 90%. The situation in, sorry, this is Puerto Rico, this is Peru, the title is wrong. The situation in Peru seems to be more challenging, as from 1 to 8 loons, there is a clear pattern that the more loons you throw into the area, the better the coverage. But it's rather striking that from 9 to 13 loons, the density of the coverage, it doesn't seem to change a lot. Of course, if you look on the subfigure on the right, in which we plot the histogram with the number of intervals with 1, 2, 3, and 4 loons, we have some, we don't have a lot of data with that many loons. But still, it seems clear that even if you could have complete coverage with 7 loons, according to our data, it's very difficult to have these 7 or more loons perfectly placed to provide 100% coverage. And finally, for the case of Kenya, a similar figure to the ones before, there is a notable improvement. There are some extra gains in throwing more and more loons into the area, but this relation between loons and the coverage provided is not that straightforward, and sometimes you don't even see the benefits of these extra loons. To add into the guarantees and the performance of the service, we look into a recent paper by Google engineers, actually, on the meaningful availability. And inspired by that metric, we define the window maximal coverage. And the idea of this window maximal coverage is that given a time window X, we look for the window that has the best average coverage. Basically, if this N of T1, T2 of coverage is the number of pixels during that time window, we are looking for the maximum. So with the idea being, okay, assuming that I have a service time of X, what would be the best service that I obtain during X? So for the case of the toy sample illustrated in the slide, if my window of time is 1, I would pick the instant number 2 as I have full coverage. Then if my time window is 2, I would pick the second and third, as these are the one with the largest number of blue hexagons. And if the number of window is 3, then I would take the first 3, and this is the one with the largest number of blue hexagons. So this windowed coverage, of course, is decreases with the window. The shorter the window, the easiest is to find a period of perfect or very good coverage, and the longer the window, well, the average starts to decrease. With this figure, we analyzed the 3 use cases, and we could identify that for Puerto Rico, it was possible to have up to 8 hours of perfect coverage. So during these 3 months of service, there was a window of 8 hours where the whole island was completely covered by the service. Well, for the cases of Peru and Kenya, this practically complete coverage never reached 1 hour. So starting from 1 hour, you see there is some slope in which the coverage starts to decrease. Again, this reinforcing the idea that providing this service using balloons is a challenging task. If we go for the minimal coverage, which is the opposite definition, basically to look, given a window, how worst it could be, here you can clearly see that for the case of Puerto Rico, you could reach up to 5 days without any coverage in the whole island, while for the case of the regions of Peru and Kenya, you could have even 3 days with no coverage in the whole geographical area. Then we also measured how long it took from one of the hexagons since the moment it lost coverage until it received some coverage again, this outage time. So we collected for all scenarios these so-called downtimes. And then for every pixel, we computed the median downtime, the median of the time since it lost coverage until it had coverage again. And for these 3 cases, we see that for the case of Peru, the median downtime spans between 10 minutes and a few hours. For the case of Puerto Rico, it's never below 1 hour, but it's never above a few hours. While for the case of Kenya, the situation is more heterogeneous, with some pixels showing an outage time between a few hours up to 10 hours, and others from 10 hours to almost 1 day. And finally, we compared to try to assess, and this is part of an idea that we briefly explored as the paper was going the review process. We compared the effectiveness of the placement of the loons with that of a random deployment. Basically, what we did is to take the median coverage with n loons, and we compare this against a deployment in which we randomly deployed n loons and measure the coverage. So we repeated this 1,000 times. Given a number of loon n, we randomly deployed over the area these n loons and computed the resulting coverage. And with that, we compare the median coverage with the real locations that we have with the median coverage with this that we call Poisson deployments of loons, these random deployments over the loons. Basically, for the 3 cases, what you see is, alas, that the real coverage is always better than a completely random coverage, since the colored line falls below the x equal to y line for the 3 cases. But still, this line is not really far away from the y equals to x. So the service provided by Loon, it's better than a random deployment, but we guess that is not that different from the one that you would have used using a random deployment of Loons, which again proves that the challenge to provide a service with flying cell towers using Loons is a daunting one. So to wrap up, we have modeled the service that could have been provided by the Loon service using optimistic assumptions, which is interference-free model with a free space propagation model, and we didn't consider if the interloon links were available or not. And also we restricted ourselves with the areas in which we already knew there was some coverage. And our conclusion is that, yes, it's better than nothing, and it could support some sort of delay-tolerant service in which the outage periods you could endure up to several hours of periods without internet. But still, this service has significant challenges, since adding extra loon doesn't necessarily mean significantly improving the service, as some of the cases I've highlighted. Sometimes you have to over-provision your network, the number of cell towers, the number of loons by a factor of 3 to reach more than 90% coverage warranty. And in fact, the performance is not that different, let's say, to that of a random deployment. As a matter of fact, as we were submitting this paper, on January last year, Google announced that they were shutting down the Loon service, the Loon project. Well, actually, the Alphabet company announced that they couldn't find a way to get the cost low enough, so they were ready to shutting down the service. After this shutting down of the project, SoftBank acquired the patents, from the company, because the researchers have developed a number of patents on how to use AI to navigate using the wind predictions and forecasts and so on. There is also a book on the Loon experience that is freely downloadable and is script the database. And also Alphabet released all the database of the flights for the Loons, including the GPS coordinates and the sensor data. So instead of our methodology to collect the data, even if we publish our data set, also the database of all the Loon positions and sensor is available over that Zenodo recording. Well, we have more results in the paper. We also analyze some first approximation for capacity. We also analyze different channel models in case of rain or in case of obstacles. You have all the details on the paper. And that was everything that I had prepared for the talk. First, I'll start with the questions, and then I'm also open to any other question. Okay, so the first question from Andre is, please compare your architecture with federal balloon networks and hubs. Well, actually, we didn't want to do that. So we wanted to go for the purest of services with just Loons and a perfect core network, let's say, or a perfect backup for the Loons. We were just interested in the final end, in the node bits performance, provided that everything else was ideal. So this is what we wanted, and the service was so-so. Some reviewers suggested, and this is, I think, aligned with what Andrew was asking over the chat, that perhaps the Loon service cannot provide a complete internet service by its own, but it could be complement, or it could complement some other architectures that use drones, low-flying airplanes, and so on. So I agree. Our results show that perhaps for other architectures that they are being proposed with UAVs, a balloon may be convenient since it may be used to fill in the gaps, or the other way around. Whenever the balloon is not providing service, you could deploy drones for these specific hotspots to improve the service. If I failed to answer your comment, Andre, please let us know.
Thank you.
Then Maxime asked that losing a connection with a Loon may cause it to fall. Is there possible to counter this with switching Loon to Loon frequency ranges or satellite connections? I guess it is. So I don't know what they did. I know for sure that operating Loons over densely populated area is very risky, since, I don't know, the fabric of the Loon may break at any point in time. And so even in that case, if you have satellites or low frequencies, if the fabric of the Loon is broken, the Loon is going down. I guess, but this is while guessing, that if you stay outside populated areas, if you go for rural areas to poorly connected area, the problem is less critical, since you have, by definition, less people that you can crash on and less infrastructure you can crash on. But I don't know if they decided to implement some failback system to try to keep a connectivity to these Loons. Then Artem is asking a very good question, which is, when you have several balloons over the same area, then you have potentially the intercell interference. So how do they solve that, which they would even increase the challenge of providing the service? We don't know. We don't know, but in our case, we did, again, the optimistic assumption of assuming that there is no problem. If I remember okay, according to the measurements, in some cases, a pixel, an hexagon, would be able to see 3 and 4 different Loons. I would say that even 4 at the maximum. So this would be potentially interference to 4 different cells, which would be a challenging one. I don't know what they had in mind, but our main takeaway of this paper is that even if assuming the most optimistic assumptions on the service, the service is so-so, when we start adding assumptions such as the one you are proposing, Artem, then the service would be even worse because it would be even more complex to manage or filled with more interference. So this would be even worse service, a worse user experience. But we decided to stay away because ours was the first attempt to provide the characterization of the most basic service.
Thank you, Pablo. Maybe one additional question about performance of the wireless communication. So if I understood, so the packet goes up to the balloon, and then through several balloons, it goes to some gateway. So do you have some characterization how is the typical, what is the typical delay in such a system?
Yes, that's we were also quite curious. We wanted to analyze that. We don't know because we couldn't find we couldn't find information regarding these ground gateways that they have. For the case of voice communications, I think that they implemented some sort of local breakout. So in case you had a call from one loon to the same loon, in which you didn't have inter-loon communications, they were doing this local breakout of the E node B, so then you could establish a call within the same country because basically it's the same cell, so that problem doesn't exist. But then, where are these ground stations to provide the internet access? We don't know, and it would be interesting and very challenging because to estimate the service, then you would have to estimate 1, 2, 3 hops plus as these interloon communications are based on lasers. Well, as the altitude varies from 15 to 20 kilometers, well, that's a lot of altitude. So it would make the problem even more challenging. But we couldn't find where are the internet gateways for the loon service, and I'm not sure they ever released this information. I guess that by analyzing the database they released, by analyzing the heat maps of the loons, by identifying in which areas some loons don't move away, one could gather, one could guess where these gateways would be. And this is similar to the question that Ilya asked, right? Where does internet come from? Exactly, we don't know. There were some reports, I cannot find the source, but even when they were claiming at the height of the service in Puerto Rico, that they were claiming that 100,000 people were connected, and I don't remember right now, but if you Google on the internet, you'll find that they reported something like hundreds of megabytes that were transmitted. If you divide these hundreds of megabytes over the population and the number of days they were providing the service, the data rate was very small. It was kind of SMS type of speed. So but this is my personal opinion, I think that another of the challenges that they didn't probably solve was how to keep up sustained connectivity to this internet gateway. And that's why they rely, for instance, for emergency services of calls and voice communications. But that one, I have no idea. I'm sorry.
Thank you, Pablo.
Yes.
I have one more question I wanted to ask orally. So, in the end, this story sounds very sad, and it's unfortunate that Google Loon service didn't launch. But can you speculate on what could be changed and to provide at least some basic connectivity for those areas? What was missing? What are the key mistakes made?
Okay, this is pure speculation, and I think it comes down to the type of service that eventually, if you're providing a cellular service, you are paying for a service. So the moment you start paying for a service, you expect some guarantees, you expect some minimum. And my guess is that, as we have seen, this is a best effort delay-tolerant service. So the problem is that if you really try to sell this, and I think this was the idea of Alphabet, as a substitute to cellular tower, you are very doomed to fail, because a tower stays there and provides a relatively stable coverage, while a loon, that's not the case. So I think that the problem was they aimed high. This was a moonshot project to try to provide a similar service to that of 3G, and it was not possible. So I think that perhaps the decision is a business decision, that they were aiming too high for a service that is not the one that you can provide with this technology. So had they rebooted the service, perhaps they would have started with some more delay-tolerant, less ambitious service, and so on. But I guess also that they aim high to attract a lot of funding. I mean, they attracted SoftBank, invested like 120 million in the service, if I recall correctly. So they were able to aim high to attract a lot of funding for, apparently, or what they were aiming at, for a very guaranteed service. And we believe, and that's why we think our research is interesting, that relying exclusively on towers that move with no engines, by design, you should go for a different type of service, either a delay-tolerant network service or complementary service, in which, I don't know, instead of paying for a prepaid card or paying for a voice contract, you do something else. I don't know whether this is IoT-like or whether this is very backgroundish service, but the technology as it was developed, it failed to reach that high. So perhaps they aimed so high.
Okay, thank you very much.
Okay, and then this one additional question. Our database is based on the data from flight radar. Yes. So there are areas in which flight radar does not have any receiver. How can it impact your results? Oh, well, that's a very good question. How are we sure that the data is complete? We did a number of hacks. Of course, we didn't have the ground truth, so we couldn't compare with the real data set, since Google only launched the real data set once we had already submitted the paper. We did a lot of data sanitization. We did a lot of checks on identifying gaps. So whenever we were tracking a flight, we measured that from the time we see a flight, the amount of time that we keep on seeing the same flight is more or less bounded, or put it the other way around. We saw that, but this was very manual, whenever we missed a flight for a lot of time, let's say for 2 hours, 3 hours, it was because it was crossing the ocean. So, of course, our results may be missing some flights, or maybe missing some points over the data set and over the times. We will never be sure if we miss something, but given the trajectory that we were analyzing by plotting and looking at the figures, looking at the disappearance gap of the loons, that we kept this bound to a couple of hours, and looking at also our ability to track the number of the loons over the area with those reported by loons, we are quite confident that we were able to capture a reasonably accurate picture. Of course, if we wanted to formally answer your question, we should download the dataset from Google and do a one-on-one comparison with their dataset and the one we captured from flight radar.
So I guess that's all for today. Let us thank Professor Serrano for his interesting talk. I also want to thank all participants of the seminar for joining our seminar and asking questions. See you. Goodbye.
Okay. Thank you, everybody. It was a pleasure.